Have you ever stopped to think about what's really going on inside your electronics? There's a hidden rule, a simple, elegant piece of physics that powers basically everything, from your phone to the International Space Station. It was discovered almost 200 years ago, and it's called Ohm's Law.
I mean, think about it. What could a tiny phone charger possibly have in common with the massive, bright headlights on a car? They seem like they're from different planets, but they are both governed by the exact same, surprisingly simple physical law. By the end of this, you're going to understand exactly what that is.
So our story starts way back in 1827. There's this German physicist, Georg Ohm, and he's fiddling with some of the very first electrical circuits. And as he's experimenting, he starts to notice something, a consistent, predictable pattern, a fundamental relationship between three key properties. He had basically stumbled upon the invisible blueprint for how electricity actually works.
Okay, so let's break down this golden rule. To really get Ohm's law, we need to meet the three main characters in this whole story: voltage, current, and resistance. And don't worry, we're going to use a really simple analogy to make it all just click.
Okay, first up, we've got voltage, which we represent with a V. The best way to think about it is as electrical pressure. Imagine it's like the water pressure in a pipe. It's the force that's just waiting to push electricity through a circuit. So more voltage means a much stronger push.
All right, next we have current, which, funnily enough, is represented by an I. Now, if voltage is the pressure in the pipe, then current is the actual flow of the water. It's the measure of how much electricity is actually moving through the circuit, and we measure that flow in amps.
And that brings us to our third player, resistance, or R. This is anything that gets in the way and slows down the flow. In our water pipe analogy, this would be like a narrow, pinched section of the pipe that squeezes the water. The more resistance you have, the harder it is for that current to get through. And we measure it in, you guessed it, ohms, named after Georg Ohm himself.
So let's just pull all of that together for a second. Voltage is the pressure doing the pushing. Current is the actual rate of the flow. And resistance is the narrowness of the pipe slowing it all down. This simple comparison is really the key to getting an intuitive feel for how these three things are always in this delicate dance with each other. And what's so amazing is that Georg Ohm boiled this entire relationship down to one beautifully simple formula. Voltage equals current multiplied by resistance. V equals I times R. This little equation isn't just some abstract math. It's a fundamental law of physics. It tells us that these three things are completely tied together. If you know any two of them, you can always figure out the third.
Now look, analogies are fantastic for getting your head around an idea, but this is physics, right? We need to see it in action. And the beauty of Ohm's law is that we can test it so easily. So let's just run a quick thought experiment that shows how the math perfectly predicts what happens in the real world.
Let's imagine we've got a standard 9-volt battery and a common 100-ohm resistor. Now, before we even hook anything up, we can use Ohm's law to predict exactly what the current will be. We just rearrange the formula to solve for I. So current equals voltage divided by resistance. That's 9 volts divided by 100 ohms, which gives us a predicted current of 0.09 amps. Okay, so now let's imagine we actually build this simple circuit and measure it. And what do you think we find? The multimeter reads, you guessed it, 0.09 amps. A perfect match. This right here is the power of the law. It's not a guess, it's not a theory, it's a precise prediction of how electricity will behave. This reliable, repeatable truth is the foundation that allows engineers to build all the complex electronics we rely on.
All right, so it works in a perfect little lab experiment. Big deal, right? Well, it is a big deal, because this simple rule is being used all around you, every single day, to solve real, practical engineering problems. Let's look at a couple of examples that you'll definitely recognize.
Okay, let's start with your car's headlights. Imagine you want to add a feature to dim them slightly. Now, you can't just turn down the car's 12-volt battery, that's fixed. So how in the world do you control the brightness? Well, you use Ohm's law to control the current.
See, the whole secret here is that a bulb's brightness is all about how much current is flowing through it. So with a fixed voltage coming from the battery, the only way to lower the current is to increase the resistance. By simply adding a resistor into the circuit, we do just that. According to V equals IR, if V stays the same and R goes up, then I has to go down. It's the law. Less current means a dimmer headlight. It's a simple, elegant piece of engineering.
Okay, here's one you've probably even thought about. We all know that hitting an older phone battery with a super powerful fast charger isn't always the best thing for it. But what if you wanted to intentionally charge it more slowly to help preserve its health? Yep, Ohm's law is the answer.
Your fast charger is designed to push a lot of current, maybe 2 amps, but we can slow that right down just by adding a resistor to the charging circuit. That extra resistance chokes the flow, forcing the current down to a lower level, say 1 amp. The result? A slower, gentler charge that's a whole lot kinder to an aging battery.
Now, this all sounds pretty simple, and it is, but, and this is a huge but, before you go thinking about tinkering with your own gadgets, we have to talk about something incredibly important: safety. You see, resistance doesn't just reduce current, it turns electrical energy into heat. And managing that heat is the difference between a working project and a dangerous one.
And I really can't stress this enough. Understanding this next part isn't just about getting things to work, it's about keeping things from smoking, melting, or even catching fire. It's absolutely crucial.
So to get a handle on all that heat, we need one more little formula. It's the power formula. Power, which we measure in watts, tells us how quickly energy is being turned into heat. And the formula is P equals I squared times R. Now notice that I, the current, is squared. That's the part you really have to pay attention to. It means that if you double the current, you don't just double the heat, you quadruple it. That's why even a small increase in current can get dangerous really, really fast.
And this leads us to the absolute golden rule of working with resistors safely. First, every single resistor has a specific power rating, usually something small like a quarter watt. That rating is the maximum amount of heat it's designed to handle without destroying itself. So, if your P equals I squared R calculation shows you're going to generate more heat than that rating, it's going to fail. It's going to burn out, period. That's why the most important safety step is to always calculate the power before you even think about choosing your resistor.
So let's bring this all home. We started this journey way back in 1827, and we've landed in the tech that's in your hand right now. In a way, you've just gained a new superpower: the ability to see the invisible rules that make our modern world tick.
You haven't just learned an equation. You've actually decoded this fundamental, powerful relationship between electrical pressure, flow, and restriction. It's this simple, predictable logic that lets engineers design and build absolutely everything, from the simplest circuits to the most powerful supercomputers.
So, I'll leave you with this question. Now that you get it, now that you understand this basic rule that runs literally everything in our modern world, what are you going to see differently when you look at the technology all around you?
Thanks for watching. Don't forget to like, share, and subscribe for more amazing videos.